So here we are now in part C. On part C of this chapter, we're getting deeper into calculations. You're gonna have to truly remember how to do a stoichiometry for General Chemistry 1 or 1411 and apply everything you have learned so far. We're still dealing with the common ion effect and the buffer systems. So, dealing with buffers, the buffers allows you to find the pH without having to do an ice table. So in other words, the ice table is no longer required at this point because there's a formula that defines the buffers, at least to calculate the pH, and the formula is the Henderson-Hasselbalch equation, which tells us that the pH is going to be equal to the pKa plus the logarithm of base 10 of the conjugate base over the acid. Given that this is a buffer system where the conjugate base and the acid are in the same system, their volume is the same. So we can actually say that we're not dealing with concentrations anymore. Given that the volume at the top and the bottom is the same, the volume will cancel. And you can actually say that this is going to be the mole of the conjugate base over the moles of the acid. And there's a variance to this formula that you can also use, which is POH equals PKB plus log of the moles of the acid over the moles of the conjugate base. We're basically flipping everything around. So if you're ever given the Kb instead of the Ka, you can use POH, and then you know that 14 equals POH plus pH, and you can easily find the pH. Alternatively, you can totally forget about this variance of the formula, and if you're given the Kb instead of the Ka, you can say that 1 10 to the minus 14 divided by Ka equals Kb. So you can find one given the other, because remember, 1 10 to the minus 14 equals Ka times Kb, which is the same as 14 equals pKa plus pKb. So there's so many ways that you can approach a problem like this. And besides that, one more thing, remember that the P on the Ka, the P on the Kb, the P on the Kw, all those P, that's nothing more than minus log. That's what the P means, minus log. So keep that in mind. So going back to the Henderson-Hasselbalch formula. So that's the formula. So basically, you can find the pH as long as you can calculate the minus log of the Ka, and you can find the moles of the acid and its conjugate base, or the moles of the base and its conjugate acid. So super important formula to understand. So let's do a problem like this. Using the Henderson-Hasselbalch equation, pH equals pKa plus log of the conjugate base over the acid, and we're talking moles of each one of them. That should give us the pH. So what do we have on this case? Well, we have the Ka, so the pH is going to be equals to the minus log of 1.8 10 to the minus 5 plus a log of the moles of the conjugate base. So let's see if we can find that. So using the Henderson-Hasselbalch equation, we did that already. Calculate the pH. That's where we're going with this. Of a solution, so it's a mixture, made by adding 3 moles of acetic acid. So the acid, we have, not 3 moles, sorry, 0.30 moles. Remember, we're not using molarity here. There's no need because the volumes on top and bottom is the same and they will cancel. So we can just use the moles. So it's going to be 0.30 moles of acetic acid. I'm abbreviating the formula with AC. And 0.30 moles of sodium acetate. The sodium is going to be just part of the solution. So sodium acetate, for every sodium, there's 1 acetate. So you got 0.30 moles of the acetate, which is the conjugate base. And altogether, it's going to be 1 liter, which is irrelevant because the volume on this ratio cancels. So that's it. That should give us the 4.74. Let's verify. Let me pull out my calculator. 1.8 10 to the minus 5. If I find the log of that, but it's not just the log, it's the negative log, then I get 4.74. So this is 4.74 plus the log of this is nothing more than the log of 1, right? Because it's the same on top at the bottom. And the log of 1 equals 0. So this is just 0. So the pH is 4.74, given that the acid and the conjugate base were exactly the same amount. So there's no change. They neutralize each other. So that would be the pH of a buffer made with equimolar quantities of the base and the conjugate acid, or the acid and the conjugate base. So once more, we're just using the formula. pH equals pKa plus the log of the moles of the conjugate base over the moles of the acid. So with that given, you should be able to do this problem. The answer is going to be 3.77. And you can notice right away that this is not the same as that. So this is going to be a little bit different from the one I did. So let's talk about the pH range. So what is the pH range? Well, remember, if you have a solution, which is a buffer, right? You're going to have conjugate base, you're going to have acid, you're going to have conjugate base, you're going to have acid, and then every time you add base to it, the base reacts with the acid and it gets neutralized. Every time you add acid to it, the acid reacts with the conjugate base and they get neutralized, so the pH doesn't change. So for how long can that be done? Well, that can be done only around plus or minus 1 pH of the pKa. So, for example, the one we did earlier, the pKa was 4.74. So this buffer should be good enough from 3.74 all the way to 5.74. So that's what the range means. On what area is this buffer going to be good? So a buffer prepared with acetic acid will always be good around the pKa plus or minus 1, therefore 374 to 5.74. So it's a basic concept. If you know the equilibrium constant of the acid, you can change it to the pKa, and then plus or 1 minus unit is the range where this buffer is going to be able to prevent the pH from changing drastically. If you wanna do a system, for example, like the example I gave you before, where you have bacteria that thrives at pH 7 neutral, then this buffer wouldn't be good for you because this buffer is only good plus or minus 1 unit from the pKa value. So let's see how we can use that. What value of pKa does an acid has to possess to be used as part of a buffer system to study bacteria that thrives at pH 3.8? Ideally, you want to maintain it on 3.8, right? So you probably need to find a buffer around 2.8 to 4.8. That will keep it close to that point. So you're looking for a buffer that have a pKa of around 3.8. As simple as that. So if the pKa is exactly the same as the pH you're looking for, then that's good. But sometimes those acids do not exist. You're not going to find an acid that matches exactly the pH you need, right? So let's say that you have one that is 3.0. So if your pKa is 3.0, this buffer is going to be good enough for anything that you need to maintain between 2 and 4. So that buffer will work for something like this. It will be very close to the edge, but it will, if that all you have on your shelf, then you can use that because it covers that range. If you have an acid with a pKa of 4.3, then you can say, well, this buffer is going to be good from 3.3 all the way to 5.3. So that will also work for that. So that's what we refer when we're talking about the buffer range. It's always plus or minus 1 unit from the pKa value. So with that said, you should be able to do this problem. So you're going to be studying a human cell. This is the optimum for the human cell. So which one of these choices will be the best one for you to work on this? So imagine this is what you have on the shelf. So can you use that, or do you have to go to another lab to borrow from somebody else? So let's do something different now. So for 500 milliliters of a buffer solution that is 0.155 molar in this base, this two should be over here, sorry, and 0.145 molar in that conjugate acid, you got 1 hydrogen more, right? Calculate the pH before and after. Well, we know this is a buffer solution, so immediately pH equals pKa plus the log of the moles of the conjugate base over the moles of the acid. And we are given the Kb. So I want to use this formula, so I'm going to say Ka equals 1 × 10⁻14 divided by the Kb, which is 5.6 10⁻⁴. So let me find out what is the value that we have for Ka. So 1 10⁻14 divided by 5.6 10⁻⁴. That's going to be 1.78, actually 79, once I round, 10⁻11. So this number is super, super, super small compared to 1, which means it's going to favor the reactants, which is telling us that this base is not a good acid. And that makes total sense. This is not gonna react like an acid because it's not an acid, it's a base. We got it from a Kb. So this is our Ka value. 1.79, let me fix that. 1.79, 10 to the minus 11. So, and we need to find the pH before and after we add anything to it. So basically the Henderson-Hasselbalch formula with the values given. So pH is going to be equals to the minus log of the 1.79 10 to the minus 11 plus log of the moles of the acid. So how do we find the moles of the acid? All the millimoles, as long as we have the same on top and bottom. We're going to say that the solution is 0.500 liters. And we're multiplying that by the conjugate base, which is 0.155 moles over liters. And that should give us the moles of the conjugate base. We know that's not going to be negative because it's going to be a Lewis base that's going to donate the lone pairs. Divided by, we still have 0.500 liters multiplied by the molarity, which is 0.145 moles over liters of the acid. So if you notice on this case, the volume cancels, so you can just put the molarities on this case, and that will give you what we need. So in this case, we're going to have pH equals 1.79 10 to the minus 11, and we're looking for the log of that, the negative log. So that's going to be 10.75 plus 0.155 divided by 0.145, and whatever we get there, which is going to be 1.07, we're going to do the log of that. So when we do the log of 1.07, we're going to get 0.029, which is perfect because this is telling me that 10.75 is only going to change by 0.02, which is what a buffer is supposed to do. It's supposed to prevent drastic changes in pH. So the pH of this buffer is going to be 10.72. So the before pH is going to be 10.72. What about the after pH? Well, what's happening here? So this is what's happening here. I'm adding these many moles of a strong acid. So I know I have, so how many moles of the conjugate base do I have? 0.500 liters multiplied by the molarity, which is 0.155 moles over liters. That's going to give me the moles of my base. And I'm adding a strong acid to my base, so that's going to eat the base by this amount, 0.10 moles. Of the acid. So the base is going to be reacting with the acid and it's going to be consumed by the acid. So let's see how many moles of the base we have. 0.500 times 0.155. That's going to equal 0.078 moles of the base, which is being consumed by these many moles of the acid that I'm adding. So that tells me that I'm going to have 0.068 moles of my the base or the conjugate base. So for this particular case, what goes on top is going to be how much of the base remains after adding the acid to it. And the answer is 0.068 moles of the C2H5N2, which is the conjugate base, NH2. So we do the same thing with the acid. So once more, we begin by finding out how many moles of the acid I have. I know I have that many liters. And the concentration of the acid, 0.145 moles per liters. And this is an acid, and we are adding acid, so we are adding acid to it. It's not going to eat it away because it's an acid with an acid. You're just adding acid, and we're adding 0.010 moles. So when I do the calculation for my moles of the acid, 0.5 times 0.145 equals 0.073 moles of the acid, and I'm adding 0.010 moles of the hydrochloric acid. So I'm going to have 0.083 moles of the acid, which is going to be C2H5NH3Cl, or the acid. So that's going to be 0.0830 moles of the acid, C2H5NH3 plus. So when I do that calculation, what am I going to get? The minor log stays the same. And I'm going to do 0.068 divided by 0.0830. And then I'm going to find the log of that. And that's going to give me minus 0.087, which tells me my pH is going to be 10.66. So my pH after is going to be 10.66. So from 10.72, it just went to 10.66, which is more acidic, and that makes sense because I was adding acid to it. So always double check that, make sure that your calculation didn't go wrong. For example, if I did something wrong and I forgot to carry my negative value, It would have been higher, and I would have said, I just added a strong acid to it and it became more basic. That doesn't make sense. Let me check my calculations and I will say, oh, I forgot to put my negative. So always check the result to make sure it makes sense. And that's how you evaluate the pH of a buffer once you add something to it, but using the stoichiometry, the molarity, and finding out how many moles you have of each one of them. So with that said, you should be able to do this one, and so you can follow your progress. The pH at the beginning's supposed to be 4.74. After you add whatever you're gonna add to it, it's gonna be higher, which means you're adding a base because you made it more basic. Is that what we're doing? Yes, you are adding a base. So these numbers, which is bigger than 4.74, makes sense because it's more basic now. So always check for those details like that. And then after you do that, you should be able to do this one. This one you're giving a KB, so be sure you can deal with that. And with that, you have been introduced to the Henderson-Hasselbalch formula. And now you know how to deal with buffers. So that will be until the next time. When you come into the next part, not to scare you, but this is the part that every semester the students tell me this is the most difficult part of the whole course. And it's not, because you are experts on titration now, so you know how, you understand how a titration works, and you know how to do a stoichiometry like we just did. So as long as you keep that in mind and you know what's happening at every point of the titration, this part should not be difficult. So until next time when we're gonna go deep into this.